Americans eat roughly 1.85 billion pounds of potato chips every single year. That's more than any other snack on the market. Not popcorn, not pretzels, chips. And the process that gets a raw potato out of the ground and into a sealed bag on a store shelf in under 24 hours is one of the most precisely engineered food operations on the planet. Multiple production lines running simultaneously, non-stop, 24 hours a day. Washing, peeling, slicing, frying, seasoning, and packaging, all happening at speeds the human eye can barely follow. In this video, we're breaking down every single stage of that process, from the field to the bag. Let's get into it. Stage 1, the potato. Before a single chip gets made, the process starts with a decision that most people never think about. Which potato? The chip industry doesn't use your average grocery store russet. Large-scale manufacturers source purpose-grown chipping varieties, Atlantic, Snowden, and Superior being among the most widely used in the U.S. These aren't random choices. Chipping potatoes are selectively bred for a specific combination of traits: thin skin, low moisture content, and, most importantly, low reducing sugar levels. That last one matters more than almost anything else. When sugars in a potato slice hit hot oil, they undergo a chemical reaction called the Maillard reaction, the same process that browns bread or sears a steak. A little browning is desirable, too much, and you end up with dark, bitter chips that fail quality inspection before they ever reach the bag. Chipping varieties are engineered to stay sweet neutral, giving processors the tight control they need over color and flavor consistency across millions of units. Potatoes are grown under contract with major chip manufacturers, with farmers following strict agronomic guidelines on fertilization, irrigation, and pesticide use. When harvest arrives, specialized digger harvester machines run through the fields, driving steel lifter blades 8 to 12 inches into the soil. The machines comb upward, separating the potato clusters from the earth and feeding them onto onboard vibrating conveyor screens that shake off loose dirt and debris. From there, the potatoes drop directly into trailing trucks, sometimes moving up to 40,000 potatoes per minute, keeping the line continuous and waste minimal. Those trucks don't go far. Chip potatoes are time sensitive. Unlike table potatoes, which can sit in cold storage for months, chipping varieties need to reach the processing facility quickly. Extended storage causes sugars to accumulate, throwing off the fry color. Most loads are delivered and processed within days of harvest. Speed isn't a luxury here, it's a quality requirement. Stage 2, incoming inspection and storage. When a truck full of potatoes rolls through the factory gate, it doesn't just pull up and dump. Every load goes through an incoming inspection protocol before it's accepted. Quality control technicians pull random samples from each load and run them through a fry test. A small batch of slices is fried on the spot and evaluated for color using a standardized chip color chart. The result determines whether the load is cleared for production, held for retesting, or rejected outright. Loads with sugar levels that are too high get turned away. There's no workaround. Cleared loads are offloaded into large storage bins or directly onto intake conveyors depending on production scheduling. Facilities designed for high throughput operations can hold tens of thousands of hundredweight of potatoes in climate-controlled storage, maintained at around 45 to 50 degrees Fahrenheit, warm enough to prevent the cold-induced sugar conversion that happens at refrigerator temperatures, cool enough to slow any spoilage. Humidity is controlled as well. Too dry and the skins crack, creating defects downstream. Too wet and bacterial load climbs. This isn't passive warehousing. Temperature and humidity sensors monitor conditions continuously, and the storage environment is adjusted in real time. Every day in storage is a variable, and the best facilities account for all of them. Stage 3, washing and peeling. When a production batch is called, potatoes move out of storage and onto the wash line, and this first wash isn't gentle. Industrial washing systems run the potatoes through a combination of high-pressure water jets, rotating drum scrubbers, and turbulent water flumes designed to strip off soil, surface debris, and any field residue. A facility running at full capacity can process upward of 6 million potatoes through this system in a single day. The goal isn't just cleanliness, it's equipment protection. A single piece of embedded gravel that makes it past the wash station can chip a slicing blade, and a damaged blade means inconsistent cuts. And inconsistent cuts mean product that fails texture specs at the end of the line. After washing, the potatoes move into abrasive drum peelers. These are stainless steel rotating cylinders lined with rough, carborundum-coated surfaces. As the machine spins, the potatoes tumble continuously against the abrasive walls, while high-pressure water jets flush the loosened skins away. The peel is removed aggressively but selectively. The goal is clean, smooth potato flesh with minimal product loss. Removing too much surface material cuts into yield and drives up cost per pound. Exiting the peeler, each potato passes under a vision-based inspection system. High-speed cameras scanning for green spots, deep eyes, rot lesions, or incomplete peel coverage. Any potato with a defect triggers a targeted air ejector that blows it off the line and into a separate divert stream. Nothing compromises what comes next. Stage 4. Slicing. This is where things get mechanical in a serious way. Peeled potatoes drop into a centrifugal slicer, a machine that uses high-speed rotation to force each potato outward against a ring of stationary razor-sharp blades positioned at the perimeter. The centrifugal force is consistent, the blades are fixed, and the result is a potato that's sliced into uniform rounds in a fraction of a second. The target thickness, right around 0.055 to 0.065 inches. That range isn't arbitrary. Slices thinner than that curl, fold, and fry unevenly. Slices thicker than that don't cook through properly, leaving a dense, under-crisp center. The texture that defines a good chip lives entirely in that narrow window. Blades are swapped out on a regular schedule, not when they fail, but on a proactive maintenance cycle based on the number of potatoes processed. A dull blade doesn't cut cleanly. It compresses the slice slightly before cutting through, which damages the cell structure of the potato and leads to oil absorption issues during frying. Different blade profiles produce different products. Straight blades produce the classic flat chip. Corrugated blades with a regular wave pattern produce ridged or wavy chips. The blade change is the only mechanical difference between a classic and a Ruffles-style product. Everything upstream and downstream is the same. Right after slicing, freshly cut chips drop into a high-velocity water flume that carries them forward while simultaneously rinsing off surface starch. Starch is the enemy of a clean fry. If it's not removed, the chips stick together in the oil and clump into irregular shapes that fail the optical sorter downstream. Multiple rinse cycles, including a soak stage and overhead spray jets, ensure the slices arrive at the fryer clean and starch-free. Stage 5. Frying. The continuous fryer is the centerpiece of the entire operation, and it's exactly what it sounds like. A single unbroken frying vessel that can stretch 40 feet or more in length, through which potato slices move on a submerged conveyor, fully immersed in hot oil from entry to exit. Oil temperature in a continuous fryer is typically maintained between 340 and 375 degrees Fahrenheit. The slices enter wet and cold, immediately triggering intense steam release as the free moisture in the potato vaporizes. That steam is what creates the bubbling you see in any fryer, and it's actually doing two things simultaneously: cooking the potato and creating the porous internal structure that gives a chip its crunch. As moisture leaves, oil enters, replacing it in the cellular structure of the slice. Fry time sits around 2.5 to 3.5 minutes. But it isn't fixed. Every batch of potatoes comes in with slightly different moisture and sugar levels. The fryer's control system monitors oil temperature, chip color sensors at the exit point, and moisture readings in real time, making continuous micro adjustments to conveyor speed and oil temperature to hold the product inside spec. A batch with higher than normal moisture content gets a longer run time. A batch running high sugar gets a slightly lower temperature to prevent over-browning. The machine is making these calls thousands of times per hour. Oil management is equally critical. Used frying oil degrades, it darkens, its smoke point drops, and it transfers off flavors into the product. Chip manufacturers maintain a continuous oil replenishment system that adds fresh oil at a controlled rate while drawing off used oil, keeping the oil blend within a defined quality window at all times. Fresh-only oil counterintuitively produces inferior chips, New oil foams excessively and causes uneven browning. A managed blend is the target. Stage 6. De-oiling, optical sorting, and salting. Chips exiting the fryer are golden, crispy, and carrying more surface oil than the finished product spec allows. They move immediately onto a vibrating de-oiling conveyor, a shaker table that agitates the chips gently while excess oil drains away through the mesh below. The vibration here is calibrated carefully. Too aggressive and the chips crack. Not enough, and the oil retention is too high. From de-oiling, the chips enter the optical sorter, one of the fastest inspection systems in any food production environment. High-resolution cameras scanning at hundreds of frames per second analyze every chip in the product stream, checking for dark spots, burnt edges, folded chips, or any surface defect that falls outside the color and shape tolerance window. When a reject is detected, a pneumatic air jet fires at precisely the right millisecond to blow that chip out of the stream and into a divert chute. The timing precision required here is measured in milliseconds. Salt application comes immediately after sorting, while the chips are still hot. Finely ground salt is applied through a volumetric dispensing system, typically a rotating drum or an overhead cascade, that distributes a thin, even coat across the entire product stream. The residual heat from frying is what makes salt stick without any binder or adhesive. The chips are their own glue at this point. For flavored varieties, barbecue, sour cream, and onion cheddar, a tumbler seasoning drum replaces the simple salt cascade. The chips enter a large rotating barrel where powdered seasoning blends are continuously dispensed. As the drum turns, the chips tumble through the seasoning cloud, picking up an even coat on both surfaces. The rotational speed and seasoning feed rate are controlled to hit a specific seasoning-to-chip ratio by weight, usually between 8 and 15% of the finished chip weight, depending on the flavor intensity target. Stage 7. Weighing, packaging, and palletizing. From seasoning, chips travel by bucket conveyor up to the weighing system. And this is where the engineering gets quietly impressive. Multi-head combination weighers, units with 14 to 32 individual weigh heads arranged in a circle, receive product from a central dispersal cone that distributes chips across all heads simultaneously. Each head weighs its own small portion of product. A central computer runs continuous calculations, identifying which combination of heads adds up to the target bag weight within the tightest possible tolerance. The winning combination dumps simultaneously into the fill chute below. The entire cycle repeats multiple times per minute, per packaging line. The result is bag weights that hit target with an average giveaway of less than half a gram per pack, a number that represents millions of dollars in yield savings at production scale. Filled chips drop into a vertical form-fill-seal machine, a unit that simultaneously forms a bag from a flat roll of packaging film, fills it with product, and seals the top and bottom in one continuous motion. Just before the top seal closes, a nitrogen flush pushes an inert gas charge into the bag, displacing oxygen. The nitrogen does two things. It prevents oxidation, which causes staling, and it creates the internal pressure that cushions the chips during shipping. That air pillow everyone complains about. That's structural engineering. Sealed bags are conveyed to a check weigher for final weight verification, then to metal detection. Any bag outside weight spec or triggering the metal detector is automatically rejected before it ever reaches the case packer. Approved bags are counted, collated, and packed into corrugated shipping cases by automated case packers. Cases are sealed, labeled, and transferred to robotic palletizers that stack them in precise interlocking patterns on wooden pallets. Completed pallets are stretch-wrapped and staged in finished goods storage, ready for outbound freight. From a seed-selected potato bread specifically for its sugar profile to a sealed nitrogen-flushed bag sitting in the chip aisle, the entire process runs in under 24 hours. Every stage is instrumented, monitored, and automated to a degree most people never consider when they tear open a bag. The fry color, the slice thickness, the seasoning ratio, the bag weight, all of it is engineered output, not chance. That's what it takes to produce billions of pounds of a product that has to taste exactly the same every single time. If you found this breakdown useful, subscribe. There's a lot more of this kind of content on the way.